So the next presenter is Rocío Rodríguez. He's for the Aalborg University, assistant professor there. And the title of the talk is Broadband Dielectric Characterization of Materials and How to Design Low-Loss Glasses for Packaging Applications. We go on with the presentation of Rocío.
Hi everyone, my name is Rocío. I come from Aalborg University in Denmark, and today I'm going to talk about, I will show you the broadband dielectric characterization of silicate materials and how we use those results in order to design a low-loss glass for packaging applications. So first I will introduce the facilities in Aalborg University. So we have this is our large anechoic chamber. As you can see here, we can put a car inside, and yeah, the car goes up in this elevator. We cannot open the wall and the roof. So if we want to do some measurements with a drone line, we can open the chamber and just measure. We have here, this is the transmitter antenna. We have it over here. And then we have also a beam tree arm that can go around the car if we want to do some measurements.
Pablo, this is your goal for the next.
I'm thinking about that. I have the zone where buying the terrain. Thinking.
Then we have this target chamber that can measure until 18 gigahertz, and it has like different probes around. And here we have the antenna under test. And then we have a compact range chamber that can go until 60 gigahertz, and here we have the antenna, and there is a reflection here. For material characterization, we have the same one that you have here from spec, and then we have this split cavity resonator. That you see below. This is the lid, so you can put the sample inside and then you close it, and it looks like this. And then we have this MCK from Swiss tutorial. It's basically two corrugated horns inside here, and then you put your sample, and here you will connect to the frequency extenders, and this one can go from 60 gigahertz until 110. In our section, we are three groups. I will talk about the antenna group because it's the one I'm more familiar to, but there is also another group, propagation group, that does channel sounding, and they have like this 128 massive MIMO array. And there is also a machine learning group that does all sorts of applications from bio to RF design. And in the antenna group, there's been a lot of small antennas and arrays designed, especially for Wi-Fi phones. Also large antennas and arrays, lately RIS, meta surfaces, and bioelectromagnetics. My research, for the PhD, I started my PhD during when 5G came out. So I was dealing with the integration of antennas in the mobile phones. Here you can see the iPhone. And as you can see here, in the iPhone, there are usually three 5G modules. So they have two of them in the sides here, and then one below the glass cover. So as you can see, what they did is to cut a window in the metal, and here they cover it with some plastic, and then they put the antenna module behind. So the solutions I was trying to propose, it was to make this the frame more robust, and instead of cutting a window, they just proposing other solutions to deal with this. Then I also look to the other module that goes below the rear cover of the phone, and this is glass usually. And as you can see here, when you put some glass on top of the antenna, you can detune the S parameters, and also you have a loss of gain of around 3 dB. And this is in the best case scenario. In the worst case scenario, you can actually split the beam in two, so you won't have the antenna pointing in the direction that you want. It will be in other directions. So what I did is to propose some meta surfaces, one here below the antenna, like on top of the antenna, and actually make the beam look again like the one that fails this. So this is one of them. It's double glass layer metasurface, and this is the radiation pattern in free space. This is just the glass, and this is again with the metasurface. So, but today I'm not going to talk about that. I'm going to go in a different direction, and I will talk about the dielectric properties of glass. So, to introduce the motivation about this, if we go up in frequency, then we can see that the losses start to increase. This is something very surprising that I saw. This is a presentation from a group in Japan, and they actually show that above 250, SAW has higher losses than coplanar waveguides. So it is first we need to characterize the loss of the materials, and then we need to actually select a proper guiding structure. So what I did is, well, this is from their paper, and you can see here that from 250, the losses of the SAW are higher than the inclusive line. So if we split these losses into the electric losses and conductor losses, then you can see that the dielectric losses start to increase more than the conductor losses from this 200 gigahertz. And so why is this interesting for packaging? So usually what we saw in the industry, it was like system on chip. So you have a silicon chip and you have all the solutions in your chip. But this, since we are reducing our solutions, the transistor cost and complexity are increasing, and the performance is not that good. So the industry is tending to system on package. What happens here? We have many different packages, many different materials. So there is a mismatch between the electric characteristic and also the thermal characteristic of the material that affect the reliability of the whole solution. So in that sense, glass is a very promising material because actually we can tune its properties in order to improve the reliability. So, and also glass, we can design it with low permittivity, so you reduce the coupling between adjacent conductors, and it can have lower cost than fusilic, for example. And yeah, we reduce this thermal expansion by tuning the coefficient of thermal expansion. So, yes. How does a material look if we think about from the material science perspective? So the electric properties can be divided into the real part of the permittivity and the imaginary part of the permittivity that is related to the loss tangents. So depending on the frequency, we can see here that there are some relaxations and there are some resonances as we go up in frequency. There are no, in the literature, it's not possible to find this, where does it happen? So our main goal for this study was to characterize actually where, at what frequency was this ionic resonance happening, and how was impacting the dielectric properties in the millimeter wave spectrum. So yeah, the details from the ionic polarization can affect our dielectric properties over here. And this is the this is the setup that I use at Penn State University. Some of the techniques are single frequency techniques. Some of them can actually provide a broadband spectrum. And we try to cover as much as we could. And yeah, I will show next or not.
I don't know why.
It's okay. I can say my word. These are resonant techniques, which means that they are more accurate in terms of giving the epsilon and the loss tangents. This is a transmission reflection technique, and this is also transmission reflection, and this is FTIR that I will show you in a few slides. Why is it the resonant technique more accurate than the transmission reflection? Because we are we have a cavity and we calculate a Q, so we have a resonance, and we actually calculate how wide this resonance is and how much does it move from the resonant frequency of the cavity alone. And with that, we can obtain the epsilon. Yeah, this MCK from Swiss to 12 is just two corrugated horns, and this is time domain spectroscopy that is with laser. So we actually have two crystals here that when you impinge them with some femtosecond pulse laser, they can produce terahertz light, and that is what you measure at the end. And it doesn't show the example anyway.
I'm so sorry, because perhaps this is a version of the PowerPoint that you have.
Yeah. It was too heavy, probably it didn't copy. Anyway, well, you measure in time domain, then you do the Fourier transform, and you compare both spectrums, and that you can obtain the epsilon and loss tangent. For FTIR, you have an interferometer that it basically measures the interference. And so these are the measurement results. The until 2 terahertz, I will show you more after. So I have divided the materials by families. They are all silicates, but these ones in blue are glasses. Glasses have usually a dielectric constant between 5 and 7. It depends on the elements that you have inside of them. And this one is Borofluid that has a very low dielectric constant. Then we have the few silicas are more pure than glasses, so it means that they don't have as many modifiers as glass, and they have a low dielectric constant. And last, we have quartz here. Sapphire is not a silicate, but it's just there for reference. So for the loss tangent, this is for the dielectric constant, and I will go to the loss tangent, yes. So the glasses have the higher loss because they are the least pure of them. And you can see it's around 10 to the minus 2 in all the frequency band, and it increases an order of magnitude as we move to the terahertz. Then we have the few silicas, they're 1 order of magnitude lower, and then we have the crystalline materials that are like quartz. And what happens if we move up in frequency? So if we move up in frequency, we find what we were looking for, the ionic resonance, that happens around 13 terahertz. And we found another peak, and this peak is called in literature boson peak, and it's a quasi-localized vibration. And this is the ionic resonance I was trying to, we were looking for, and it's due to the bending of the silicon, oxygen-silicon bonds. As you can see here, there is a huge difference between the dielectric properties in the lower frequency bands, but as we move up in frequency, all the values are quite compact compared to each other. And yes, I will mention it, sorry for going back and forth, but I will mention it here. This is the loss tangent. As you can see, for the few silicas, they have a very low value. And then we have the glasses here, and as we move up in frequency, they are all together. What I wanted to add is that in the boson peak, when we have materials with higher amount of modifier, where like glasses, that peak is higher for the glasses. But if we go to the ionic resonance, then the more pure your material is, the higher the peak. So you can have a loss tangent of 40 for fixed silica. At that. So it's a very good absorber if you want to use it at that frequency. This is a sum of the what I was just mentioning. So why do we have a difference in these materials? They are all silicates. So it has to do with the internal structure of this material, and that is called Q speciation. So if we look at the quartz, for instance, this is crystalline, and it has all the silicon units are connected to oxygen, and those oxygens are connected to another unit. So basically, the whole structure is made of these Q4 units. For fused silica, we add some modifier, and you can see that the network here is more amorphous. So when we apply an electric field, it can move, and that is what produces our losses. And when we have a glass, then this network starts to disconnect in places, and we have the elements that we are adding here connected to the oxygens. And yeah, this graph is just to show that if we increase the amount of modifiers that we add in our network, then the structure becomes more like it's made full of these lower Q units. So what we were thinking is, if we can decrease the polarizability of my material, then we can obtain lower loss. Yeah, I will skip this. And if we look at this table over here, a glass is usually composed of a network former, that in this case is silicon, and modifiers. Modifiers are in the first two columns, alkalis or alkaline earth, and those are connected to the network. But by itself, they cannot produce a glass. So they need this element like silicon and oxygen. So we said, why, instead of having these elements that have very high polarizabilities that you can see in these numbers, why don't we use boron that has the lowest of all of them? So what we did is we replaced those elements with boron, and as I was showing earlier, here the silicon is connected to 4 oxygens. The boron connects to 3. So you can expect that the connection is not going to be perfect. So boron has a coordination number of 3, and the silicon have a coordination number of 4. So they will have like islands. That is what is called phase separation. So you will have islands of 3, and then also like the silicon will be on one side and the boron will be in another side. That is why it hasn't been pursued for the companies. We see in the literature that there are different materials that also use boron in their composition, but the higher that we see, it was 13%. And yeah, so we melted the powders, and then we pour it here. This is me closing the furnace, and we tried with different compositions of boron. So we have 33% boron, and you can see the phase separation like more clear in that one. And then we have higher percentages of boron, and we can get these samples over here. So if we measure, this is the graph I showed you earlier. This is our solution. It has lower permittivity than any of the other silicates that we measure, including the fused silicas. And if we look at the loss tandems, then here we have glasses above, and then we have the fused silicas. So our solution is right above the fused silicas for being an amorphous material. And then we look in the microscope to see if it was actually phase separated. And we see these islands that are, some of them are silicon rich and some of them are boron rich. And we also can plot depending on we measure in this microscope, and it can actually color your graph depending on the element. So you color the silicon in pink and the boron in blue, and you can see over there how is the distribution. And yeah, that's all from me. Any questions?
Thank you.
Thank you very much. Really nice presentation. Thank you very much. So we have now time for questions. If any.
So in the end, you need also some chemical knowledge.
Yes.
Not just ready.
Yeah, this part I did while I was in Penn State University. I spent 2 years there learning a bit about materials, but yeah, I still lack a lot of knowledge.
And when you were doing this characterization, did you there was the possibility actually to study possible inhomogeneous, non-homogeneous, or anisotropy, because when you do materials, you can introduce it unwanted.
Yeah, actually I didn't show, but I designed a metal surface on glass, and it was supposed to, one of them it was supposed to transmit, one of them was supposed to reflect, and we actually measure with the MCK, and you can actually guess the S parameters, and from that you can get the epsilon. So it's possible to characterize.
Then, I mean, when you do this synthesis, you can get an undecided inhomogeneous behavior, and then it's very undecided.
But this was like very small scale. Yeah. So these are like the islands. I think it was like 1.5 microns. So if you compare to the RF, the wavelength is way larger than the this over here. Yeah.
Thank you.
Okay. One curiosity about the moment you were preparing the glass. This is in the
US, but in Denmark we can do it too. Yes.
Yeah. My first question is if we can buy something similar, but just because. Okay.
It's a furnace.
No.
So
not so easy, Pablo. This is another.
I'm thinking about, but.
So fused silica melts at 1,700 degrees. So that is why they don't use fused silica, because it's very expensive to heat at that temperature. But with glass, you add modifiers to lower that melting temperature.
Okay.
So your furnace has to go a bit below, like 1,400, 500. So you just need to find a furnace. Then you also need a crucible. I think the material is rhodium. That is also very expensive.
Okay.
Like 20,000. Just buying the powders, and you mix the powders, and just put it in the furnace.
Okay. Another curiosity: when you get the ionic peak or the position that you said, okay, you have a perfect absorber and a structure that the more pure your elements are, you have the highest peak. In terms of physics, it goes to heating the glass.
A lot of movement between the ions, and then I think it heats.
So if you touch, you find it that it's hot, because when I think in absorption, I think where the energy is going. Is the only.
Yeah, probably. We haven't tried the.
Okay. Yeah. So perhaps an experiment for winter is to have this in the glasses of your house with in terahertz.
But
perhaps a reactor, an energy reactor outside your house to heat. But okay. Okay. Thank you very much. Anything else here from, or also from the audience?
I was surprised for the Swiss 212 resonators, because Swiss 212 began as a
manufacturer of printing
manufacturing, and now they are completely changing the business.
But when you buy, they make it for you. Like they don't have like a solution that you can just buy and stuff. They make it specifically with what you order for them. Yeah.
And you pay specifically.
You pay much more.
Yes.
So, and you did a training for.
For that, I needed training. Well, you need training for everything there in the US. But it wasn't that hard. I mean, I wasn't grabbing the thing myself. I could have done so, but I was just helping with you also need to cut, because it was very viscous. So I was cutting with the scissors.
To get closer to that facility.
Yeah. What you need more training is for this.
Y luego que si tenemos quemaduras los brazos.
This one requires a very hard training in order, because it's very expensive equipment. Like
The microscope you mean for
the SEM,
I think Oh, this is the one that we have just bought.
Oh,
Yeah.
I'm going to make an stay in Madrid.
Because we received last week this microscope, and was amazing things that you can see. Yeah.
Okay, perfect. If we have any question from the audience in Google Meet, or we go through the next presentation. Well, thanks again, Rocío, for the talk. Okay, thank you.